So we can convert Maxwell's equations from differential to integral form using two theorems, namely Gauss and Stokes theorem. Before that, let's just write down Maxwell's equations in differential form, which are fairly straightforward, but just in case anyone forgot, let's just write them down and define them. So to start, we have Gauss's law, which just says the divergence of the electric field is equal to the charge density over the permittivity of free space. And for the magnetic field, we have the no monopole equation, which says that the magnetic field has no divergence. Now, Faraday's law, the curl of the electric field is a changing magnetic field. And then the Ampere-Maxwell law says that the curl of the magnetic field is equal to the permeability of free space times the current density plus the Maxwell correction term, which is mu naught epsilon naught, changing electric field. So it's good to understand this form first before moving on. And now we can define Gauss and Stokes theorems, which will help us convert between the two. Basically, we need Gauss's theorem for the dot product terms, the divergence terms, and we need Stokes' theorem for the curl terms. So let's define the Gauss theorem, which just says that the integral over a volume of the divergence of some vector over its volume is just equal to the surface integral of that vector dotted with its area. And then Stokes' theorem gives us a relation between the surface and the line. So if we say that the integral of the curl of some arbitrary vector dotted with its area is equal to the closed line integral of that vector. And with these two theorems, we can get to the integral form of Maxwell's equations. So just starting out with Gauss's law, if we integrate each side over the volume, so if we just do integral d tau, then we find that the surface integral of the electric field dotted with the area, and now let's think about this right side for a second. So we have rho, we have the integral over v of rho over its volume. So this is just going to equal, if rho is charge over volume, then the integral over that volume is just the charge, because rho is basically q over v. If we times that by v, then we just get q. So this is just going to equal the enclosed charge over the permittivity of free space. So then Gauss's law in integral form reads so let's just number them 1, 2, 3, 4, and that's 1. So for 2, pretty simple for the magnetic field, since it's 0 for the divergence, then it's its surface integral is also 0. So that one's fairly trivial. Now we need to use Stokes' theorem for the curl terms. So for Faraday's law, if we integrate Faraday's law over the area, then we see that we get a line integral and that's going to equal negative ddt of the surface integral of b dot dA, and this should be just the, well, it shouldn't be closed there. This is the integral over an open surface. Okay. Because this, if this were closed, then b dot dA would be 0. So integrating b dot dA over an open surface is non-zero. That's the magnetic flux. So this is just negative ddt of phi b. If we define phi b to be the open surface integral of the magnetic field dotted with the area. So Faraday's law in integral form reads E dot dl, which can be thought of as a sort of potential, equals negative d phi dt. And then we can actually just write one more term here just to find that as the EMF that's valid to do. But remember, it has units of potential, so it's not necessarily a force. And lastly, for the Ampere-Maxwell law, if we take the open surface integral of the Ampere-Maxwell law, then we get a line integral in B. We get integral over S of mu naught J dA dot dA plus mu naught epsilon naught integral over S, got the ddt outside too, mu naught epsilon naught ddt integral over S of E dot dA. Again, open surface, not closed surface. This term is just the electric flux, and the integral over the area of the current density is just the current. So this term becomes mu naught times the enclosed current. So we have the closed line integral of the magnetic field is just equal to mu naught times the enclosed current plus mu naught epsilon naught d phi dt. And we can also define mu naught epsilon naught as 1 over c squared. So the Ampere-Maxwell law in integral form becomes one over c squared d phi dt. So those are Maxwell's equations in integral form. from differential form using Gauss and Stokes' theorem.